Hey students, how we doing? You guys never answer anymore. It's like you don't answer. It's too awkward. Okay, fair enough, fair enough. So I'm going to go through the solutions of in-class assignment 10.4, the chapter review. Hopefully this can help you on your test and life in general. I'm not going to write down what the problems state. Hopefully you have the worksheet in front of you, and I'm not going to rewrite the problems here on the worksheet. So let's get to it. Part A, number one, part A. All SAT scores follow a normal distribution with a mean of 1800 and a standard deviation of 150. Part A, draw a bell curve. This should be easy to all. This is old school. This was so 2015. But again, that's a zero, believe it or not. That was a zero. Again, we're going to add and subtract two standard deviations. That is 150. I don't have room, but here's two standard deviations. That's going to be 2100, and two standard deviations to the left is going to be 1550. Fine, I may as well finish it. 650 is one standard deviation, and here 1950 is plus one standard deviation. All right, part B. What is the probability that one randomly selected student scores over an 1850? So we're kind of saying, what's the probability that one person has a score of over 1850? Is this unusual? Well, it shouldn't seem very unusual because it's way less than one standard deviation greater than the mean. But let's calculate it. We'll normal CDF, and we're looking from our lower limit as 1850 to our upper of infinity. The mean is 1800 and the standard deviation is 150. And plugging and chugging these in my calculator, I got 36.94. And is this unusual? No, this is not unusual. Not at all. Quite likely, actually. Wouldn't be unusual at all. 36 point something % chance of it happening. Not unusual. Okay, part C. Sorry, did I go too fast? It's YouTube. You can pause and rewind and fast forward. Just have to pull out the file from the VCR and make sure the tape doesn't get stuck. Alright, we will sample part C. We're going to randomly sample 100 students. How do we know that the sampling distribution of X bar follows a normal distribution in this case? Actually, this is two reasons. Either one would suffice. Number one, sample size is clearly over 30. We're sampling 100 people. So this again is the idea of the central limit theorem. And the central limit theorem says that anytime we have a sample over 30, the distribution of the sample means should be approximately normal. And that's nice. But you could have also argued, and either one would work in this case, that the population, that says pop, that the population also follows a normal distribution. Only one of these has to work in this case. Both of them do. Two is better than one, right? Alright, part D. What is the mean and standard deviation of the sampling distribution? Well, this was this fancy looking formula. Mu of X bar equals mu. And what does that mean? That means, in this case, what is mu? 1800. That is the average of all the average is going to equal 1800, which is the average of all the test scores. And if you think about that intuitively, it makes sense that, hey, if I took a whole bunch of samples of 100 and if I averaged them all together, even the averages of all those averages should be pretty darn close to, in this case, 1800, which is the average of the entire population. But the standard deviation now is maybe not so intuitive, but maybe it's intuitive that it's going to get smaller, it's going to be less, because we're not dealing with one person now, we're dealing with 100 people whose average score, and we're looking at the average score, of 100 randomly selected people. So in this case, it's going to equal the standard deviation of the population, which was 150 divided by the square root of the sample size, which in this case was 100. So that's going to be 150 over 10, or 15. So this is going to lead us to part E. asking us to sketch a bell curve of the sampling distribution of x bar, including 2 standard deviations, plus or minus 2 standard deviations. So again, this is going to represent all the sample means of choosing 100 people. So, hi Black Cat. So for instance, what we mean by this, for instance, is that using the empirical rule, 68% of observations should be within 1 standard deviation of the mean. That is, if I did thousands and thousands of samples, I would expect that 68% of them, for instance, 68% of the time, I'm going to get an average SAT score somewhere between 1785 and 1850. And and 95% of the time, I should get a score between 1760 and 1830. So you can already tell just having an average either over 1830 or under 1760 should be somewhat unusual. Yeah, that's part F, right? So part F says we take a simple random sample of 100 JSerra students and obtain a sample mean of 1850. Okay. If we consider this to be a random sample from the population, is this unusual? Justify with an appropriate calculation. Well, I could already, number one, going back to that bell curve I sketched in part E, kind of go, well, this is definitely well over 2. It's actually over 3 standard deviations to the right. So this should be fairly unusual. Isn't that right, kitty cat? Alright, they're not in a talking mood. They're just walking all over my papers, but they're not talking. But they're here. I got home, made it home from school, got to my iPad, trying to make you a video of this solution by popular demand. Okay, so I'm going to use the standard deviation of that and the mean of that bell curve that we sketched in part E. So that had a mean of 1800 and a standard deviation of 15. So I'm pretty much going, okay, what's the probability we get something 1850 or greater, which we already kind of said was well over 3 standard deviations to the right of the mean. So this should be a quite unusual event. So we'll normal CDF. And I'm going from 1850 to infinity and beyond. Make sure you put lots of 9s now because we got 4-digit numbers. And the mean was 1800 and the standard deviation was 15. So when we crunch those numbers, I got 4.29e negative 4, or 4 zeros, and then that number 4209. Is this unusual? Yes, it's unusual, very unusual. But you guys are unusually good anyway, right? JSerra is unusually an awesome school. So, yeah, it's unusual. All right, moving on. Numero dos. That's Spanish for number 2, if you didn't know that. You work for the Department of Game and Wildlife, and you're in charge of setting limits of the number of fish that fishermen are allowed to keep. Recently, there's been concern about the health of the yellowfin tuna population. If the average weight of the adult tuna is under 30 pounds, then the tuna could be overfished, leading the Department of Game and Wildlife to lower the limit of fish that fishermen are allowed to keep. Otherwise, the limits will stay where they are. So you take out the boat and you go out and catch 15 fish. So we'll consider this a random sample of yellowfin tuna. Oops, I forgot to close my parenthesis there. In order to perform, so you go out and catch 15 fish to perform a hypothesis test. The results are on the next page, so you're looking at all those numbers, intrigued. So part A, state the appropriate null and alternative hypothesis, define your parameter. So here we're going to go that mu, the mean, is going to equal 30. So we're going to, again, the null hypothesis, we're going to assume that the claim is true, or that they're 30, or even, you don't need that little inequality sign, but that they're at least 30. They could be more than 30, no problem. But what we really want to kind of watch out for in this case is for the alternative hypothesis is that they're under 30. So I just like to often kind of rewrite what this stuff means. Maybe in regular terms. So if I would conclude the null hypothesis, I would say I'm essentially saying that the fish population is okay. right? That they're not overfished. But if I come to the alternative hypothesis, then I'm saying the fish population is overfished. So this is going to help me, especially in part B, where I'm going to find type 1 and type 2 error. But let me define my parameter first, where mu is going to equal the true average weight. I'm going to put the true because it represents all of the population. It's a parameter. The true average or mean weight of yellowfin tuna. Delicious fishes. Ooh, my cats would like that. Oh yeah, they would. Alright, so that's part A. Part B asks, what is type 1 error and its consequence? So let's go back and look at the null. Let's go back and look at let's go back and look at our hypotheses. So we say that a type 1 error is when you reject the null hypothesis when it was true. So I always remember type 1 is kind of the easiest. I just remember that the null hypothesis was true the whole time. You just end up rejecting the null when it was true. So what would that mean in this case? So we reject the null hypothesis. That actually means we're going to come to the conclusion of the alternative hypothesis when the null hypothesis was true. So we're going to, for a type 1 error, we would conclude essentially that the fish, or the tuna, let's replace that with tuna actually, or that the tuna fish, or that the yellowfin tuna, that the tuna are overfished, when in reality, excuse my writing here, when in reality the population is okay. And I'm abbreviating mostly because you wouldn't ever do this on the test, I know that. But I'm abbreviating because I'm short on time and I don't want to spend a whole lot of time writing. What's the consequence? Well, what would happen in this case? We conclude that the population is overfished when in reality the population is okay. So we would, and I'll put in the word needlessly, we would needlessly, because I guess we didn't really need to do it, needlessly lower the fish limit. Needlessly implying that we didn't have to do it, that we were wrong doing it. But you know what? That's not so bad, right? What's a type 2 error? So again, look at all hypotheses. So type 2 error is when we fail to reject the null hypothesis when it was false. In other words, we kind of come to the conclusion of the null hypothesis, although I kind of say watch out with that. But this is kind of why it's nice writing these in kind of layman's terms. So so we would conclude essentially the null, or that the population is okay, when in reality they're overfished. So we would conclude the fish population, or the tuna population, is okay, when in reality they're overfished. And what's the consequence? The consequence is that we would further, or how about we would be further, no, I was fine where we are. We would further deplete the fish population. So, Part D asks, based on your answer in Part B and C, what would you set as your significance and why? And this was kind of part of Monday's lesson. So we're asking ourselves, what's worse, committing a type 1 or committing a type 2 error? Okay, so type 1, what's the consequence? We'd needlessly lower the fish limit. Okay, so you couldn't catch as many fish, but the population's going to be okay, right? Part C is we would further be depleting the fish population. In other words, we'd still be catching a whole bunch of fish and wouldn't change the limits when in reality they were actually already in danger to begin with. That sounds worse to me, and especially since I work, read the problem, I work for the Department of Game and Wildlife. I'm on their side, right? So to me, a type 2 error is worse. So part D, since a type 2 error is worse, since the consequence of committing a type 2 error is worse, of committing a type 2 error, I'm going to just write cursive here, is worse, I would use an alpha equals what level? Should I use 0.01, 0.05, 0.10? When to use what? If I use 0.01, then I'm not going to be likely to commit a type 1 error. So if I really want to avoid a type 1 error, I'd use a 0.01 level. If I really want to avoid using a type 2 error, I would set a 0.10 level. If I'm if I don't think one's worse than another, I'm going to use a 0.05 level. Well, which one do you think is worse? Yeah, me too. Type 2, right? We don't want to keep fishing, adding insult to injury, if you will, to the poor fish. So I'm going to use a type 1. I'm going to use a type 1. I'm going to use a 10% significance level. Might mean I might make a type 1 error sometimes. More often, I'm more likely to commit a type 1 error, but I can live with a type 1 error in this case. Less likely to commit a type 2 error. I don't want to do that. Part F. Calculate the test statistics. And this is where I'm going to pause the video and see it and enter these numbers. I missed part E was the random normal independent condition. I got to do that. But anyway, I got to put all these numbers in my calculator, so I'm going to pause the video. Hopefully you already did. Okay. So again, hopefully you have all those numbers in your L1 of your calculator. And then we're going to part F. Somebody doesn't know their alphabet. Somebody doesn't know their ACBs. I've always been terrible at ACBs, but yeah. All right. Part E, check the random, normal, and independent condition. Random, again, we're going to assume the 15 fish are random, like they're random fish from the population. Independent, weights between fishes are independent. One fish isn't going to the weight of one fish isn't going to influence the weight of another fish. Like the weight of one fat black cat that I'm looking at right now doesn't influence the weight of his orange brother. Or maybe it does because he eats all his food. Yeah, I'm talking to you. Don't give me that look. Sorry, I'm talking to my, not you. I'm talking to my black cat. Sorry. Okay, the normal condition. Nothing's wrong with Mr. Bessling. He's fine. He's fine. Okay, so here is the histogram. We put all those numbers into L1, and then we plot our histogram, and it looks a little something like this. And you go, oh, is that normal? Is it normal? Well, it's good enough. Okay, it's roughly symmetric. It's kind of mound shaped. I know it looks a little bimodal, but you do have to respect too with these histograms. Sometimes it's the way the classes are arranged. If I were to make, instead of using the class length being this long, if I were to use that long, I'd actually get a totally different shape. To me, what are we looking for mostly? We're looking for, is this roughly symmetric, but more than anything, if it were really skewed or if there were a lot of outliers, we couldn't use this. So since the histogram above, I was going to write cursive, is not, oh, that's so much faster, is not skewed, nor, that says nor, are there outliers, the normal condition is satisfied or met. Condition. It's still hard for me to write on these stylus. Condition is met. Like my handwriting wasn't bad enough. I got to write with this funky little pen. Whew, I thought we were done. Man, still going. All right, part F. Calculate the test statistic and x bar, s sub x, p-value. So I'm going to go here. Let's do this. We're going to go to stat, scroll to the right to calc. Number 2 is a t-test. We're going to choose a t-test. Now the mu naught, okay, I'm sorry. First thing I want to do is input. We're going to use the data since I entered all the data into L1, right? So for mu naught, we're going to use 30, and if you're not sure what number to put there, maybe you're confused by the experiment we did today with using 0, but we use whatever the value of the null hypothesis is, or either hypothesis, so it's 30. List, L1, hopefully don't have to change that, and now mu is going to be, remember this is our null hypothesis here, our alternative was that mu was less than 30, so we're going to choose mu is less than mu naught, calculate, and here are our results. We have t, that's our test statistic, negative 1.789. Our p-value is going to equal 0.0469. Our sample mean was x bar. That, my friends, is 28.125. That's the average of all the fish that I caught. And the standard deviation of the fish is going to equal 4.19. N is 16, but that also means that the degrees freedom is going to equal 16 minus 1, or 15. Okay. So part G, state your decision, and the decision is either reject or fail to reject, and then the conclusion. And then the conclusion is a little more detailed. When I ask the conclusion is answer the question that we started with. We asking, is there convincing evidence that the mean yellowfin tuna weight is under 30 pounds? That's the answer. That's when, and then I put don't answer that yet. Well, now it's time to answer that question. So since the p-value is, which I'm going to put here, you don't have to write it quite like this. That was 0.4694. Is less than, remember what I used for alpha? I used 0.10. Since my p-value is less than alpha, you can write that in a whole bunch of ways. Cursive, go faster. We reject the null hypothesis. So answer the question that I asked. Is there convincing evidence that the yellowfin tuna weight is under 30 pounds? There is convincing evidence. That word says convincing, that's my cursive. Evidence, that's an E too. Just kidding, that didn't look like an E. Cursive is so hard. Evidence that the mean tuna weight is under 30 pounds. That says pounds too. So that's the decision, that's the conclusion. You know, wrap it all up. If you had to go to your boss, you know, you wouldn't just go to your boss, we reject the null hypothesis. Your boss would be like, what are you talking about? I don't understand. Okay, part H. Ask for a 90% confidence interval. So let's go to our tests. This is going to be a T interval. We're going to use the data L1, the confidence level 0.09. 0.90, and my 90% confidence interval is from 26.287 to 29.9 0.63. If I can repeat that and do a 95% confidence level, and I get something just a little different. I get 25.891, and this time including 30.359. So I kind of wanted you to look at this here, and in part I ask you, does your confidence interval support your conclusion? Explain. Well, so if that value of 30 is in my confidence interval in this case, and I get that value of 30 from the null hypothesis, if that's in there, then that means that's one of my reasonable estimates for, in this case, the average weight of tuna. All right, of tuna fish. So for a 90% confidence interval, you see I'm 90% confident the true average weight of yellowfin tuna is between 26.287 and 29.96 pounds. So 30 isn't in that interval. At a 90% level, confidence level, I could kind of reject that claim. But if you see with the 95% interval, it just kind of squeaked in there, didn't it? I bring this up probably needlessly, or I don't want to make things more complicated. On the test, they'll be pretty cut and dry. But pretty much the moral of the story is that these confidence levels line up to our levels of alpha. It just gets a little more complicated whether it's a one-sided or two-sided test. But for instance, since we used a one-sided test where alpha equaled 0.10, I'd actually to test that same claim, I'd actually want to use an 80% confidence interval. I shouldn't even be going here. I should stop right now. Quit while we're ahead. It won't be on the test. But this is why, long story short, at a 90% confidence level, we see clearly that that supports our claim. Not so much at a 95%, but it kind of makes sense with our p-value being, I don't want to say high, but our p-value being pretty close to 0.05. We've seen lower p-values in this case. Alright, quit while I'm ahead. Speaking of quit while we're ahead, I hope that helps for the test, and I can't wait to see you guys. And alright, I can't wait to see you guys ace this test, because I think you can do it. Alright guys, thank you.